So, good morning, students. Last time you have learned the chemical kinetics introductory part of the chemical kinetics, and you have learned what is the rate of reaction, what is the rate law, what is the rate constant, what is the order of reaction, what is the molecularity of reaction. Okay, then here there are two types of reactions, very fast reactions and very slow reactions. And here chemical kinetics, it deals with the reactions which takes place with moderate rate. Okay, then chemical kinetics, it deals with the study of rate of reaction or velocity of reaction and the mechanism by means of which a reactant it will get converted into product here, and the graph of concentration versus time. Here the concentration of reactant it decreases with time. This is the nature of the graph with respect to concentration of reactant, and the concentration of product it increases with time, and this is the nature of the graph. And the rate of reaction, it is the rate of change of concentration with time. So reaction rate, it is the rate of change of concentration with time, and average rate of reaction, it is equal to change in concentration of reactant or product divided by change in time. So the rate laws for elementary reactions, the reaction rate can be predicted from the molecularity, and in case of multi-step reactions, the rate law must be determined experimentally. The concentration dependence can be complicated one in case of chain reactions. Then the rate of chemical reaction is dependent on reactant concentrations, the state of reactants, that means whether the reactant is in solid state, liquid state or powder state, then temperature and catalyst. Here the concentration of reactant it plays important role in the rate of reaction. Usually rates increases as the reactant concentration increases. There is a increase in rate of reaction with increase in concentration of the reactant. Then the temperature it has pronounced effect on the rate of reaction, and as temperature increases the rate of reaction also increases. Again the presence of catalyst. Here a catalyst is a substance which increases the rate of reaction without being consumed in the overall reaction, and such a catalyst is called as positive catalyst. And some substances are there that do not take part in the reaction but they decreases the rate of reaction, that catalysts are called as negative catalysts. Here this is the graph for concentration of reactant, and this is the for concentration of product. Here dc by dt, it is the rate of reaction, the ratio of change in concentration with change in time, it is the rate of reaction. Then we will see what is the molecularity of a reaction. Here molecularity of a reaction means the number of ions or atoms or molecules involved in the rate determining step or rate limiting step is called molecularity. The molecularity will be only whole number and never zero or fraction. Molecularity can be determined by a reaction mechanism, but it cannot be determined experimentally. In no chemical reaction, reactants are directly converted into products in a single step. Initial reactants are converted to final products occurred by different internal steps. These steps are called elementary step reactions. The sequential representation of elementary reaction step in overall chemical reaction is called reaction mechanism. Suppose, for example, we have A as a reactant and it gets transferred into B, and B, it is our supposed product, and this conversion of reactant into product, suppose it is a three-step reaction. In first step we have A, it gives 2x. In the second step we have 2x reacts to form 2y, and in the third step this 2y they gives B, and suppose this is the rate determining step or slow step, and in this case the slow step it is the rate determining step. That means among all three steps there is a elementary step with least reaction. This step is called a rate determining step or a rate limiting step. Remember, here when the conversion of reactant into product, it will take place in number of steps. Then the rate determining step is the slow step reaction. Okay, then the unimolecular reactions means there is only one reactant take part in the chemical reaction to form product, and its rate law equation we can write a rate it is equal to K into concentration of A. That is, rate of this reaction depends on concentration of the reactant, and here it is one reactant. Then in case of bimolecular reaction, there are two molecules take part in the chemical reaction. Either that two molecules are same or different, and the rate of this equation it depends on the concentration of the two reactants. So according to the rate law equation we can write rate it is equal to K into concentration of A into concentration of B, or K in bracket A square, that means concentration of A square. And in case of termolecular reaction, three molecules take part in the chemical reaction, and either three molecules are same or three molecules are different, or two are same and one are different. Here termolecular reaction means there is a three molecules they react to form product, and the rate law equation here in this case we have rate it is equal to K in a bracket concentration of A into concentration of B into concentration of C. In this case K it is equal to rate it is equal to K into concentration of A bracket Q, because we have three molecules of same species. Therefore concentration raised to 3. And here we have two A molecules and one B. Therefore rate it is equal to K in a bracket A square into concentration of B. Okay. So in trimolecular reaction there will be collision of three molecules. And this is the another example. Suppose we have two NO molecules and one O2 molecule. It produces two NO2, nitrous oxide molecule. Then the order of reaction. Here the number of atoms or molecules whose concentration change determines the rate of reaction. That number it is called as order of reaction. Here this, or alternatively the order of reaction is the sum of the powers of concentration terms in rate equation. The sum of the powers of concentration terms in the rate equation is known as order of reaction. Or order of reaction may be given with respect to all participating reactants, in which case it is called order of reaction. Suppose for example, consider a reaction in general reaction. Suppose we have m moles of A reactant plus n moles of B reactant. We have m moles of A and n moles of B. They react to form product. Then we can write the rate equation as rate it is equal to K into concentration of A raised to m, because we have m moles of A and m it is a coefficient of this A into concentration of B raised to n, where n it is the coefficient of this B. Therefore, the total order of this reaction it is equal to the sum of coefficients of the concentration terms in the rate law equation. Therefore, we have the order it is equal to m plus n. This is the total order of the reaction. Remember well, the order of reaction it is the number of either atoms or molecules whose concentration change determines the rate of a reaction. That number it is called as order of reaction. Then the zero order reaction. Here the rate of reaction it is independent on the concentration of the reacting species. Such reactions are called as zero order reaction. I repeat, here the concentration it is independent. Okay, when the reaction rate is independent of concentration of the reacting substance, it does not depends on the concentration of the reactant substance. Such reactions are called as zero order reaction. Then the first order reaction, that means the rate of this reaction depends only on the concentration of the single reactant. All such reactions are called as first order reaction. Okay, then the examples of first order reaction. Here N2O5 it gives N2O3 plus O2 molecule. Then hydrolysis of hydrogen peroxide, we have here H2O2 it gives H2O plus 1 half O2. And decomposition of calcium carbide, here we have CaCO3, it decomposes into calcium oxide plus carbon dioxide. These are the examples of first order reaction, because the rate of these reactions it depends on the concentration of single molecule. Such reactions are called as first order reaction. Then we can distinguish between order and molecularity of the reaction. Here order it is the sum of powers of concentration reaction terms in the experimentally determined rate equation. And molecularity, it is the number of molecules or atoms or ions which must collide simultaneously in order to bring about the chemical reaction. Then order of reaction can be 1, 2, 3, 0 or any fractional number, and molecularity, it may be either 1, 2, 3 only. It cannot be 0 or fractional number. Then the order of reaction, it is determined experimentally, or order, it is an experimental quantity, and the molecularity, it is a theoretical quantity and depends on the mechanism of the reaction. It is applicable to the elementary as well as complex reaction, and the molecularity, it is applicable to only elementary reaction. Then for complex reactions, order is determined by the solvent step, and the order and molecularity of the slowest step are the same. And in case of molecularity, for complex reactions, the molecularity has no meaning. Then, before going to start with the first order reaction, let us see somewhat in detail the rate of reaction. We will see in detail what is the specific rate, its dimension, and the units. See here the rate constant or specific reaction rate. Rate constant or specific reaction rate. You know, according to the law of mass action, the rate of chemical reaction is proportional to the concentration of reacting substance or to the product of concentrations of reacting substance. Consider the reaction. Suppose we have X plus Y, they are the reactants and they produces product, and if Cx is the concentration of X and Cy is the concentration of Y at any time t, then minus dC by dt, it is the rate of the reaction with respect to concentration of reactants. So we have written the negative side, it is proportional to the concentration of X into concentration of Y. Or minus dC by dt, it is equal to K into Cx, that is concentration of X into concentration of Y, where K is the proportionality constant and is known as rate constant or velocity constant or velocity coefficient or specific reaction rate. Here this K, it has different names as rate constant, velocity constant or velocity coefficient or specific reaction rate. And specific reaction rate is a constant at a definite temperature for a given reaction. Remember, rate constant or specific reaction rate, it is a constant at a definite temperature for a given reaction. Then see the definition and dimensions of velocity constant or rate constant. You know, as a velocity of a reaction is the change in concentration of a reactant in unit time. Therefore, it has dimensions of moles per liter per second in CGS unit and mole per dm cube per second in SI unit. The rate or velocity constant is defined as the velocity of a reaction when concentrations of all the reactants are unity. Then the unit of velocity constant K depends on the order of reaction and it is determined as follows. In case of first order reaction, velocity or rate it is given by here minus dc by dt, it is equal to k into c, where k it is the proportionality constant and c it is the concentration. And from this equation we can write k it is equal to minus dc by dt into c. If we express the concentration in terms of mole per dm cube and time in second, and again concentration same unit. Here the numerator term mole per dm cube and denominator term mole per dm cube, it get cancelled and we have the unit of k, it is equal to second inverse. This is the unit of rate constant of first order reaction. Then in case of second order reaction, here we can write the rate it is equal to minus dc by dt, it is equal to k into c square, where k it is a rate constant and therefore we can write k it is equal to minus dc by dt into c square. Then here we express concentration in mole per dm cube, time in second and concentration square, therefore mole per dm cube bracket square, and here one concentration term it will get cancelled with the denominator and we have dm cube into mole inverse into second inverse is the unit of rate constant of the second order reaction. And in general, for a reaction of nth order, K will be expressed in the units of time inverse into concentration raised to 1 minus n, where n it is the order of reaction. And by using this formula, you can find the dimensions or unit of any order of the reaction. And for the next lecture, you will learn the kinetic derivation of first order reaction. Thank you. Thank you for your patient listening.